Good afternoon, or of course, good morning, good evening, wherever you might be joining us from today, and welcome to another PV Magazine webinar. This is Mark Hutchins, editor at PV Magazine, coming to you on a slightly chilly afternoon here in Berlin. A big thank you, first of all, to everyone joining us today, and of course to all of our speakers and everyone behind the scenes who has worked hard to put together such a great program on back contact technology for today. A very interesting and informative hour it is sure to be as well. As I just mentioned, we are diving today into the world of back contact technology, and in particular metal wrap-through modules. This is the technology that's already in production in Europe and in the USA, as we will hear shortly, and is gaining market share in the rooftop segment, and expected by many to have a major role to play in the future of PV also. So we're very happy to be able to take a closer look at the innovations behind this technology today. First, though, I would like to see if our audience feels the same way. So we are going to ask a quick question to all of our listeners. That should be popping up on your screens right now. So the question is, first of all, back contact cell or module technology is A, already being used in our company or institute, B, on our technology roadmap for the future, 3, interesting, I would like to learn more, or 4, not of interest for me. Hopefully we won't have too many clicking 4 in this webinar today. But while we'll give you a minute or two to answer the question, and on hand, first of all, to tell us some more on and give us some background on the technology, we have Hugo Schutt, Director of Strategic Partnerships at DSM Advanced Solar. DSM, of course, is our partner in producing this webinar today. So Hugo, just briefly now, where is back contact technology at today in terms of commercial development?
Okay, first of all, thanks for organizing this webinar, Mark. Welcome to everybody online. We have a very nice audience, going towards 200 people already. I think this is the perfect moment to share the latest developments in back contact technology, because you see the technology is really gaining momentum lately. And there's been, in the last 2 or 3 weeks, several announcements of new entrants on all main continents. So in China, we see Jolywood made an announcement of going into IBC, and the US Violet Power announced entering into cell and module production. In Europe, Energera going into IBC. So this is all demonstrating the increasing interest in this technology. And this also is reflected in very healthy growth numbers, and I will share some of those later in my presentation. I think it is, like you said, fueled by growing market demand, first of all, so especially from the residential segment, and I will also show some numbers of that. The technology is becoming more mature, and there is a growing number of suppliers of the key components, so cells, conductive backsheets, but also of the automated assembly equipment. So the customers really, the module makers really get a choice of technology and vendors. And we see that there is a true ecosystem developing. So this is what the industry needs to really make a breakthrough of this technology.
Okay, absolutely. And I think, Hugo, we see now, almost 90% of you have voted. And we see now the answers up on the screen. So it's a good chunk of people here already working with back contact technology, and over half of you saying that it's interesting, you'd like to learn more, which is exactly what we're trying to do this afternoon.
So I have convert the last few that are not interested yet.
just 1% on that one, yeah. Okay, more coming up from Hugo very shortly. And following on from Hugo today, we will hear from Paulo Macario, the President and CEO of Silfab Solar. Silfab has been manufacturing back contact modules over in the USA for a little while now. And Paulo will share some of his experience working with this technology at scale, and also some performance and durability data to share with us as well. And then we will head back over to Europe for today's final presentation, which will come from Radovan Kopacek of ISC Konstanz. Along with industry partners, ISC Konstanz is bringing another back contact module into large-scale production over in the Netherlands, based on its Zebra IBC cells, on which they have worked hard to bring down the costs of back contact. Which I think is fair to say have historically been a stumbling block for the technology. So that will be today's webinar. And as always, please do send in your questions for all of today's speakers. You can send these via the live chat function that's up and running with GoToWebinar today. And I will be feeding questions into the discussion after each of the presentations today. So please don't be shy, and we will try our best to get through as many of the audience questions as we can in our 1 hour slot today. One question that I will quickly answer now is that yes, the slides from today's presentations will be available afterwards. These are emailed out to all those who registered, and you can listen back to the webinar again at your leisure on our website. That is pv-magazine.com/webinars. Okay, and I will now hand over to Hugo Schutt of DSM. Hugo, please tell us some more about DSM's work with back contact.
Okay, thanks again, Mark. So I will give more a general introduction. I would like to go to the next slide, Frederike. Yes, there it is. So outline of my presentation, shortly introduction what DSM is doing in solar. Then for those who are less familiar with back contact technology, a short introduction. Some market numbers and trends, tell a little bit about our own product that we are selling to this industry, the conductive backsheet, and then show you some results of a use case that we did to demonstrate real value of the technology. So DSM, Royal DSM, our company, we're a 120 years old company almost, based in the Netherlands, but truly multinational, as you can see in the graph bottom right, 22,000 employees spread out all over the world. Our sales is roughly 9 billion in 3 main market segments, in materials, in animal nutrition, and in human nutrition and health. The company, in spite of the situation this year, is doing quite well. Last year we had an EBITDA of 1.7 billion euros, and this year we will be very, very close to that number. Our activities in solar, so we are a unit within the DSM Innovation Center. We're called DSM Advanced Solar. So we are providing solutions to the solar industry, mainly materials. Different groups we have. We're market leader in coatings for the glass, the top glass. We have anti-reflective coating, both for OEM applications and for retrofit applications. And we have anti-soiling coating. Furthermore, we have an innovative backsheet material. We call it the Endurance backsheet, which is very sustainable, fluorine-free, recyclable. And last but not least, our conductive backsheet, which is the topic of today. So short introduction of the technology. Basically, there are 2 different back contact technologies, metal wrap through or MWT and interdigitated back contact, IBC. On the left, you see a conventional cell, typically 5 busbar PERC cells, which are most commonly used nowadays, which is interconnected using tabbing and stringing. In the middle, you see an MWT cell. These cells have a very fine metallization pattern on the front side, but no busbars. The electrons are harvested by the thin metal fingers and then guided to the backside of the cell via holes in the cell or vias, which are filled with the conductive paste. Those are the small dots that you see. So the contact is then in the end made in the back. On the right, you see a picture of an IBC cell. These have no front side metallization at all because both the P and the N contacts are located on the back. And Radovan will tell later on more details about this technology. Also, module technology is slightly different than conventional. So on the left, again, a conventional module where the cells are interconnected via tabbing and stringing. On the right side, you see a back-contacted module, in this case, an IBC module. The front side of the module is identical, so also an aluminum frame, cover glass, and the front side encapsulant. But then instead of normal cells, in this case, you have IBC cells. And the main difference is also in the back side. Instead of a normal encapsulant, you have what we call a rear perforated insulator sheet. And in the back, a conductive back sheet. And I will tell a little bit more about the functions of those two later in my presentation. So what are the real benefits of back-contacted cells and modules combined with the conductive backsheet or CBS? Basically, it comes down to that we maximize the module power density. So that is the output of the module per surface area. And there are several factors contributing to that. First of all, because the front side metallization is minimized in the case of MWT or not present at all in the case of IBC. So you have more cell surface available to capture the sun, so you have a higher cell efficiency. There are no bus bars in tabbing and stringing, so also less shading. Very importantly, there is no soldering step to connect the bus bars with the tabbing and stringing, so very low stress and also low temperature processing, which gives a higher reliability during the module lifetime. Then next, when making the module, the cells are interconnected with this conductive backsheet, which has a very good conductivity and virtually no resistive losses. So the cell to module losses are minimized. So again, also combined with the higher cell efficiency, you get a higher module efficiency. And last but not least, the aesthetics are much better than conventional modules. The metallization is less visible because it's smaller or not at all present in the case of IBC, so you can really create an all-black module appearance. This IBC or MWT cell interconnection is obtained during the lamination process. During this assembly process, which is typically completely automated, a conductive adhesive or solder paste is applied on either on the cell or on the conductive backsheet, and then the stack is made with this perforated insulator, the cell, the front side encapsulant, and the glass, and this is all laminated or fused together in the lamination step. So the temperature is not higher in the whole process than the lamination step. Some market numbers and applications. With back-contacted modules, we typically aim at the high end of the market. The high end of the market, and that's typically the residential rooftop segment and the small commercial segment, which are what we call space constraints. So the end user has a certain amount of space available. It's not like you're in a desert or something, but you have a certain amount of square meters and you want to squeeze out as much as possible kilowatt hours from that space, because typically also the electricity tariffs that they can get are quite high. So you need high power density, so a lot of kilowatt peaks per square meter. Also, demands are high aesthetics, especially in the residential segments, and there are weight restrictions. So you cannot use these huge modules that are made currently because they're simply too heavy to lift up to the roofs. So traditional PV modules don't meet these requirements. Conventional 60-cell modules, the power is simply too low. And the high power modules with 72 or even more cells, or the super large cells, are too heavy. And also the aesthetics of these modules is not fantastic. So this is what we aim at. And this growing demand is reflected in market numbers, and these are not our numbers. This is taken from consultants like IHS and the ITRPV roadmap. What you can see here is while the average PV market is growing still with a healthy 8% per year average. And of course, we have a small dip this year due to the Corona crisis. but everybody expects that this will be repaired next year and that the market will grow again afterwards. You see that especially the residential segment, but also the commercial segment is growing much faster even. So residential is estimated to grow even at 18%, so more than twice as fast as a general PV market. And this is driven by policies by governments, so net metering, requirements for near zero energy buildings, nice electricity prices, which are expected to go up even, need for the grid security, but of course also driven by better modules becoming available. And this is also resulting in a strong growth, expected growth of back-contacted modules, shown in this graph. At this moment, we estimate the market, or we don't estimate, this is also coming from the IDRPV roadmap. The market share of back contact is roughly 4%, so 4 gigawatt out of the roughly 100, and it is expected to grow within 10 years to 16 gigawatts. So a factor 4 growth, while the total market will only grow a factor 2, or only grow, it's still nice, but 15% per year versus 8% for the average market. So there's really a lot of market traction here. So a few words on the DSM conductive backsheet. So that this is our contribution to this technology. It is a new cell interconnection concept. So it is an integrated cell interconnection with the backsheet. On the right bottom side, you see an example of a 2x2 mini module design that can be used. So this backsheet has a patterned metallization to separate the P and the N contacts on the back of the cells. And on top of this backsheet, you place this perforated insulating film to separate these contacts from short circuiting. The contact between the cells and the CBS is made by filling the holes, again with the electroconductive paste, adhesive, or low temperature solder paste. And this design and this technology offers a high flexibility in design, and it is in principle compatible with all different cell configurations. And it is fully compatible with the automated low stress pick and place cell layup equipment, which is available. And you also get thus a very high freedom in module design. Low stress cell interconnection, as I said before, there is minimal cell handling and there's no stress on the cells, low temperature. And this also enables the industry to really go to cell thicknesses below 100 microns. And we have run tests already with our partners testing such thin cells, and we have proven that you get a perfect module with such cells. So this gives a real opportunity for additional cost savings. Of course, the backsheet is flat, dimensionally very stable because you need a very precise alignment. Sustainable, it is lead-free electroconductive adhesives. Again, very low resistance losses, so a very good cell to module factor. And what I didn't mention yet, and Paolo will get back to this in his presentation, because of this metal foil in the backsheet, you get also an excellent heat dissipation in the field. So the operating temperature of the module is in practice lower, but Paolo will give more details on that. So finally, to the last part of my presentation, a use case. So what's in it for the module maker? What's in it for the end user? So I want to present a snapshot of a large study we have executed with the German strategy consulting firm Apricum. Together we have built a large tool to calculate the cost of ownership and value creation of different module technologies. In different applications. We can do a lot of simulations with this tool and vary a lot of parameters, cell parameters, module parameters, layout of the module of the system, and then next calculate power generation depending on the location, type of installation, and in the end, the money, the value that is created. And we've done a couple of those simulations. I'm going to show you one example. If you're interested, contact me, and we can do such an exercise also for your specific situation. In this study, we always take conventional module technology as a base case. So conventional PPERC in a 5-busbar cell interconnection layout. And then we compare it with different cell technologies, for instance, with NPERT or TOPCon, semi-heterojunction, IBC, metal wrap through, and so on. And we compare it with different cell interconnection technologies. So ribbons, multi-wire, conductive backsheet, shingling, paving, and tiling. And we try as much as possible to compare apples to apples. So the case study that I will show you now is based on identical cells to start off with. So we took PPERC cells with a given efficiency and compare different interconnection technologies. The cell size in this case was M2 format. And we did the case study for a module consisting of 120 half cells. But again, we can also do this for full cells or more or less cells, whatever you want, or larger cells. So the first outcome of the study, this is calculating with the assumptions of the cell efficiency and the cell to module losses and so on, the power density, power output that you see in the last two rows. And what you see here, when we compare for a given cell, different cell interconnection technologies, you see that with a conductive backsheet, you can achieve the highest power density and the highest power output. For ribbons, which is the reference case, you would end up with a power of the module of 340 watt peak and a solid 20 watt peaks more when using a conductive backsheet. What we then do next is we take a typical installation, and in the example I'm going to show you, it's an installation, a rooftop installation in Germany of a given size, where we again compare modules with these different technologies, and we calculate the additional output based on the higher power, but also on other factors like this lower operating temperature. This output we create with a standard feed-in tariff into real money. So then you see with the additional cost of the different technologies or different costs versus the higher output, we can calculate how much value is created. And we make assumptions how this value is divided over the players in the value chain. So we have assumed a certain percentage can be captured by the module maker. And what you then see is that with the modules with CBS half cell layout, you can capture the highest value. You create the highest additional value versus 5-busbar. So the 5-busbar module technology here is set at 0. And what is above, you create more value for the module maker. So higher cost of the BOM is offset more than that with the higher margin that they can get with the premium. That's not only for the module maker, also the homeowner, the owner of the system can create more value. And also again here, when using a CBS, a conductive backsheet with metal wrap through combined, you can create the highest value as owner of the system. And that's again a combination of the higher initial module power plus the improved module operating temperature. So I've used up all my time, I believe. So back to you, Mark.
Thank you very much, Hugo, for a comprehensive overview there on our back contact technologies. Okay, well, we will save questions for the end, I think. Please do. It seems we have a bit of a quiet audience so far. Please do keep your questions coming in for today's speakers. We will have some discussion after the presentations today. For now, though, I will hand straight over to Paulo, President and CEO of Silfab. Paulo, please tell us some more on your experience manufacturing with back contact technologies.
Sure. Thank you for the introduction, Mark, and Hugo, thanks a lot for starting to warm up the audience to the beauty of the technology. From my point of view as let's say a CEO of a manufacturer, I will try to provide a bit more perspective on both the beauty of the product and to a certain extent the beauty of the process. Why do I believe that we have somewhat qualified to do that is because again, during our 35-year of history and being at this point the second largest manufacturer in North America, I would say that we have pretty much seen most of the processes and most of the error that you can make in a process. And on the second point, being Silfab consistently one of the most quoted and one of the most sold brands in the residential in the United States, and having the fortune to be serving pretty much all the largest residential installer and as well as the distributors. I believe we have a reasonably understanding, or we are reasonably in tune with what the demand is and what the product or the best product for the market may be. To get some scale or some understanding of how we got to be, I guess, the second largest in North America, and how we got to play with a lot of processes and product, I need to go back to this eye chart, if you want, that explain how we ended up over 35 years and plus of history to be possibly the only consistently profitable and debt-free brand in the industry. And I would point to, I would say, mainly three periods in this chart. One period that I would call it the European one, from 1981 to 2010, when we arrived to the shores of North America. All this period, I would say, they are still maintaining the same constant, let's say, characteristic of one, a huge amount of growth. Second, innovation pretty much above all. And third, maintaining for our customer state-of-the-art, both in terms of product performance, but also product quality. So, but the first period was indeed the European one. And even during the European one, we were already, let's say, we were already playing in the early 2000s with just selling mono when everybody else was selling multi, right? Then later on, we were the first one, I believe, in 2014 to start, or 2015 to start supplying bifacial cells in North America. And the reason why I'm pointing to that is not only because being the first tends to be our way of operating, but also because at the time we were offering a cell that Rado later on will be discussing, that was the Bison cell bifacial, that was actually a precursor to the Zebra cell. So the pathways to get to the Zebra cell, to an IBC and to a back contact was already set at that time. The second, again, highlighted date that I put on this chart, it's pretty much related to 2019. And I'm mentioning that not only because 2019 was certainly a better year for humanity than 2020, but because it's when we actually launched let's say, the back contact in North America. And indeed, how did we do that? You have heard from DSM before. We created a joint venture with DSM specifically to design, to develop, and to produce in mass volumes and to market and sell those PV modules to North America. And how do we do that? We operate currently in one of our facilities in Bellingham, Washington. We operate a Eurotron line that is fully dedicated to the back contact product. Let's talk about the product itself. Some of the benefits were already highlighted before by Hugo, no question about that. But let's see, let me tell you a bit more of why our customers are seeing it as a premium, so to speak. I would say that the first 2 points, again, the first one was discussed by Hugo. The second one is going to be discussed by Rado. So let's concentrate on let's say, on the orange bullet points. Orange just happened to be one of our customer, our corporate colors. And I will get in more detail later on. But the highly automated manufacturing that has always been our prerogative now is go to an even different level by eliminating the stringers and a lot of the deposition of those stringers by robots. Something that I do love is the concept of being able to have this, what is basically a printed circuit board, extremely flexible and extremely high customizable. From a product point of view and from a customer point of view, it should be extremely important, the fact that the durability is extreme. The fact that you have that, let's call it lower stress by soldering cells, allows you to get to thinner and thinner cells that as expected and continue to remain a way to reduce the silicon. And I believe you already mentioned great thermal performance. So we'll see it later on how much, but the product is, the module is running cooler and is certainly great. Lower cell to module losses, easy to optimize for different design. We'll get into all that in detail. And by the way, by saying this, I'm not trying to slam or to say that, let's say, a properly designed and a properly manufactured, properly tested conventional module is not great. They are, and as a company, Silfab continue to invest heavily in, let's call it conventional modules, because certain characteristics like the bifaciality still is not reachable with the back contact. But you do need to be able to do everything really well to have a similar performance on the conventional module. This module, if you want to see it, is something that makes the process and the product to a certain extent simpler and faster to design and to execute. And you know that simplicity is something that we are all looking for. Now, those are the positive. What about the negative? Certainly, any new manufacturing technology requires a learning curve. Boy, our team has done an amazing job in learning and executing extremely fast. So nothing particularly concerning in there. The other aspect, though, that requires a lot of, let's say, alliances and a lot of friends, because you are going to be using, and we have started using 2 years ago, a non-conventional supply chain. So some components, like indeed the printed circuit board, rather than, or as we call it, the back sheet, the conductive back sheet, or even that separator, that the rear perforated insulator, are elements that did not exist. Is not something that you can buy at the supermarket. So it's extremely important to have those partners, and to have those partners believing in the technology, and to have those partners growing with you. Let's talk about the process again. It's always important when you manage a fairly pure play company that is dedicated to just make as many good quality products as they can possibly make, as we are. I'm going to go back. I believe Hugo already showed a couple of charts from ITRPV. This chart is just a bit of again, speaking to the flexibility of process, or the need of flexibility. Is you probably cannot read it, but there are two charts on the top. One that is what ITRPV was expecting in terms of wafer sizes in 2019, and on the right you have what their projection was in 2020. Without getting into the detail, you see that the colors are very different, but the reality is that also the expectation of wafer sizes is very different. In just 1 year, they change quite dramatically. So, and we still don't know what is going to be the future, right? It doesn't matter if it is rapid, very rapid, the wafer evolution that we're experiencing now, both in terms of size, in terms of doping, in terms of thickness, reminds, at least for me or for people of my age, it reminds a bit the Betamax versus VHS, let's say, fight for supremacy. So now we have, you start to see groups that are aligning behind, I don't know, an M10 cells rather than an M12 cell. And who knows what is going to be coming next. So the flexibility in the equipment that you buy when you're spending many millions of dollars is something that is very, dear and close to my heart, let's put it this way. And indeed, the flexibility of the back contact equipment like a Eurotron line is certainly more than what you would have with a conventional regular 5-bus bar rather than multi-bus bar line. The design itself is pretty amazing, right? When you're thinking about a printed circuit board, you can imagine a different design, and you can redesign the module, redesign the component extremely quickly. And you can adjust it to, especially when you see the deposition, that is an extremely fast and extremely cool, quick deposition of cells and gluing of cells on the let's say on the various components. You can start see how it would be easier to go from full cell to half cells to slivers of cells of a few millimeter thick, if that was what your customer and what your best design was to require. Something that is quite different and quite difficult to achieve with a conventional process. And as mentioned, this has been mentioned also before, when you are spending all your life with wires, and you see wires everywhere, it's nice not to have those wires. Again, as long as you're doing it in a very automated fashion and with really good people like we have at Silfab, we are proud of our quality, even of the conventional product, right? You know, when you see our product, that the soldering of the cells is done properly and is going to last for 30 years. Because you know that the right people and the right automation has been able to do that. But has always been, let's say, a failure mode of a conventional module. Not having that failure mode into the back contact, it's quite important, again, to, let's call it, keep it simple, stupid, as well as it is not having those cell to module losses. It's a fight for minimal gain, and cell to module losses are quite important. Let's talk, because you'll probably be waiting, okay, that's a lot of words, but what are the results? So I'm going to be quickly about when we started. First of all, we wanted to ensure that the reliability of the product was important. So we said, okay, what should we do in terms of testing? Yeah, the first 3 bullets are the regular testing that everybody will be doing. So we did that. And then we said, okay, what else could we do in terms of, let's say, shaking the tree? And we literally got the modules, well, almost literally still smoking coming out from those 3 tests. So normally they're being thrown away. And we said, okay, let's add another 600 thermal cycle to it. That is already extreme per se, and becomes even more extreme when you are subjecting modules that have already gone through all the testing. And even with that, even throwing all of that, and even trying to find how can we break them, so to speak, we couldn't. So even after all those testing and even the additional TC600, we ended up with a module that is still performing with less than 0.5% loss from the nominal. So something that I don't believe has been seen before. The other point, then let's talk about generation, how good it is. So we were expecting 2 elements to it. One was indeed, it's going to generate more in low light, and it certainly did. From a, let's say, from a simulation, we were expecting a 3%, and you see it in this chart. Practically, it's reaching the maximum between 600 and 800 watt per square meter. And the second component that we were expecting that would make the module better performing was the fact that indeed is running cooler. So if normally a module ran 47 to 50 centigrades, this one we're running from 40 to 43, depending on the design. So a 6-degree difference it's huge in terms of how much energy will be produced over time. And then again, we went through, okay, let's do PVC simulation. We did it in Las Vegas. Expectation on that climate was a 2.7% better performance in terms of generation. We did it in Boston, an expectation of 3.1%. And then we said, okay, but we don't believe necessarily that what happens in Vegas stays in Vegas. So we said, okay, let's do a real. We donated 100 kilowatt to one of our high school in Bellingham, where one of our facilities is. And we actually started monitoring the generation over time. This was the generation 1 of our module, was only a 320, while generation 3 that is launching in Q1 next year is going to be a 370. But and sure enough, we proved what we were expecting, right? We are seeing days in and days out, and since the beginning of time, a 3 to 4% increase due to those better thermal performances. So if I need to summarize, and if you have not fallen asleep, so Silfab with DSM have a joint venture that has been the first one to bring the back contact to North America. From a design point of view, back contact offers some significant advantages, and from an operation point of view, flexibility and simplicity is very important. From a customer point of view, look at the durability, it's going to last pretty much forever. And in terms of generation, it does generate more than a conventional. That's why we love our regular module. This one is indeed a premium module for us. And that's pretty much all I had to say for today. So apart from thanking, of course, for the invitation to participate to the webinar. And I'm back to you, Mark.
Thank you very much, Paolo. Some very insightful. Great to see all those thermal cycling and test results data there. Okay, we are a couple of minutes behind on our 1 hour slot, so we might run a couple of minutes over today, but I think it will be well worth it with this next presentation from Radovan Kovacek. Radovan, over to you, please. Can you hear me, Radovan?
Yes, I can hear you. Can you hear me?
Oh. Yeah, I can hear you now, yeah.
Okay, thank you very much.
Yep.
So thank you very much also for the introduction. And so I will speed up a little bit so that we have time for questions, but hopefully be not too fast for everyone. So now we have talked about great materials and modules. Let us come now to the engine of the module, which is the solar cell. And I will report you now about a low-cost IBC technology, which could be actually a game changer. And so at the beginning, I will show you some slides about IC constants, but very fast. Then about our Zebra technology, which is a low-cost IBC cell now on the market because of our great partner SPIC from China. And I will show you on one slide what we believe actually what will be the future of high efficiency photovoltaics. So at the beginning, IC constants, very quickly, we are an R&D center specializing on crystalline silicon only, and doing at the moment technology transfer to other countries. At the beginning, we cooperated with the companies like Bosch, but now you know that the music plays now in Asia, so we did technology transfer to Adani and SPIC, but now also coming back to Europe. And Paolo already mentioned that before. At the beginning, our first product was the Bison cell, which is a bifacial cell for utility scale. And so this cell came to its efficiency limits. Now we are working on the poly version of this solar cell, so-called poly Bison or Toucan. And when it's ready, we will also transfer this process. But we very fast, and we will concentrate on Zebra, actually realized that even without passivating contacts, it's possible with a low-cost IBC to go above 23%, even reaching 24% when the process is optimized. And the first technology transfer with Bisons were in Megacell, and this is also when we pushed also together with Silfab the bifacial technology to the market. But now talking about Zebra, we have a very good partner, SPIC, where we actually have proven that in mass production it's possible to go above 23.55% in average. Now we are going back to Europe, also transferring to Valoe, and there have been some news lately that now we are also cooperating with a US-based company, Violet Power, on the Zebra technology. So Zebra, what is it all about? And I mentioned already before that we can go above 23% in production in average, and what is remarkable, reaching 700 millivolts without passivating contacts. So we believe that this will be the game changer, because of course passivating contacts are out there, but not yet, let's say, cost effective. That's why it makes sense to first, let's say, use standard technology to reduce the costs and increase the efficiency of the solar cell. Then any format can be used with our Zebra technology, because we are including the 3D finger interconnection, so using isolation paste for the bus bars. We don't need any aluminum oxide. We are passivating with boron glass and then phosphorus glass, and also it's compatible to every module interconnection. Okay, and why is it so cost effective? Is because when you look at, let's say, at the standard PERC process, which is out there, we are only adding a few steps to that, and that means that we are basically leaning on the PERC process, including a couple of steps, and can go to an N-type IBC. So you need silicon nitride for masking, boron diffusion for creating the emitter, and then some wet chemistry, and also, let's say, so-damage etch. And that makes it very low cost. That means adding only a couple of equipment. A thumb rule is saying actually adding one more piece of equipment gives you 1 or 2 cents in cost of ownership. And that's why the cost of ownership of Zebra, it's, let's say, smaller than 2 times the cost of ownership of PERC, which is remarkable, because normally all the others IBC out there from SunPower, LG are more or less more than 3 times of cost of a PERC. So this slide is from the production side of SPIC, where we actually showed that it's possible to run the Zebra technology in 20 megawatt production with an average of 23.6%. And what I told you before, that we are coming without passivating contacts close to 700 millivolt, and even the best cell is approaching 24%, and having VOCs above 700 millivolt. And this module is available from Futurasan on the market using G1 wafers with 120 half cells of 350, the black version, of 360, the white version. Okay, it's cost effective, but what can we say? That actually, as for every N-type, the major drawback is the silver consumption. And so every N-type solar cells are not using aluminum as the PERC cell, but for both polarities, silver at the moment. So how can we reduce the silver amount? Is, for example, we could go, of course, to more bus bars, and at the moment we can go to 6+ bus bars. Or this is what we are now currently doing, optimizing the cell design for conductive backsheet. So actually you are putting the silver on the cell, you are transferring more or less the conductivity to the copper in the module, and that's why you can to a large extent reduce the silver content. In addition, we are also trying to use copper paste for the bus bars, and this will, let's say, give a very low cost, very powerful IBC module for the market. The very first conductive backsheet module we have produced in a European project Hercules, together with Eurotron, with already 310 watt peak at that time, which was very powerful in 2016. And now Hugo already mentioned it, there's an announcement that we will start production end of this year or beginning of next year, together with Energera, using Zebra cells and going towards 370 watts. And the question now, future of photovoltaics. So what we believe actually that for utility scale, bifaciality will still be very important. But for the rooftop market, we believe that the IBC cell will be the winner. And why? It's because it is much easier to implement the passivating contacts on the rear side than on the front side, because if you go to the front side, you have to implement selectively polysilicon on top of the solar cell, which is not very easy. So to our understanding, as we believed in bifaciality a couple of years ago, we now believe for the rooftop market and also for building integration, let's say for product integration, we are believing that IBC technology will dominate the market. And also many people are asking what will be, let's say, the next big thing after PERC. And it is possible, and we are working on it, that actually even the PERC market will turn into a poly-PERC IBC market, because as I told you before, it's not very easy to implement the passivating contacts on the front side, and because the P-type material is now using gallium instead of boron, it is possible that even the PERC market will turn to passivating contacts. So my last slide, and this leaves us also sometimes for questions, because I think that the audience is now very hungry for questions. So let us bring zebras on every rooftop.
Okay, thank you very much, Radovan. Indeed, we do have plenty of questions coming in from the audience. First of all, to kick off the discussion, though, we have one more question for you, our listeners. Thanks very much. I see most of you have stuck around for all of the speakers today. That's great to see. Okay, and now the second poll question. For residential rooftop modules, do you want to see more power, more nominal power rating, or more power output, more kilowatt hours, more energy yield for the same price? And just two answers there. And well, we see already. I think perhaps we don't even need to leave any time for for the audience to answer this question. We see well over 90%. Well, 90% exactly there are saying it's about more energy yield. And okay, I think we can pass this first of all to Hugo. Do you agree that it's the yield that's more important, and how does back contact fit into this? Oh, are you still with us, Hugo?
Yes, of course I am. Can you hear me? Yeah. No, so I agree. I would have even expected a higher response to kilowatt hours, and that stresses the importance of not just looking at the nameplate power of a module in watt peaks, but really look at also the secondary effects, which Paolo has also nicely illustrated with the temperature effect and the low light effect. So to convince the customers of our customers, so not the module makers, but the investors of the installations, you really have to demonstrate what is the value that we create. So that's why we have developed this simulation tool. And again, like I said before, we would love to do more exercises with the audience to demonstrate this.
Okay, excellent. Okay, and now on to the. One person said they clicked watt peak by mistake. Okay, on to the questions from the audience. Now, one topic that's come up a lot in the question, and I do think this was quite nicely addressed in Paolo's presentation. But what more can we say on the reliability of back contact modules? Is there long-term results from the field demonstrating this? I guess Paolo would be the first person to answer this question.
Yeah, glad to do so. As usual, for module that that have a 30-year warranty, it's you cannot point to any module that is current technology that has been out there for 30 years, right? So that is, fortunately, there are some very reliable methodologies to try to simulate or to do this, let's say, extended lifetime testing. Doesn't matter which company or which institute you're using, and they tend to be quite well designed. And as manufacturer, we all tend so to speak, first to try to shy away, but then if you are convinced as we are of your quality, to embrace it and to send your module to be tested. And it's great when they come back. So in terms of, I can only make a comparison, right? We give a 30-year warranty on our regular product, and this product was able to go beyond the normal testing. So it's if you use that proxy, so to speak, of how long it's going to last, it should be lasting longer than a conventional one. But no, there is nothing. I don't believe that there is any of this product that has been on a rooftop for more than 2 years. So there is not really anything that will convince any of us that in real life anybody has tested that long. But again, that is the same for any product and any solar module.
Okay, yeah, certainly. And I believe the tests they put them through for the IEC and beyond those standards are pretty comprehensive these days.
Yeah, it's way beyond the IEC, right? It's
yeah, of course,
is how you enter the game. But then if you're a real player in, let's say, in Series A, as we would say in Italy, of soccer, or Series C, is a big difference. You need to go through those testing.
Absolutely. Okay, and still on the topic of reliability, one of our listeners has said they have seen some information that that back contact technology is less susceptible to hotspots. Is that correct, first of all? And do you have any more detail on this, on why this is?
The answer is yes, it is correct. Do I have more details? I don't. I don't know if we are still trying to understand all the mechanisms that make it so, but we have seen exactly what the member of the audience was mentioning. So it is less susceptible. Again, in the back of my mind is not only susceptibility or hotspot, but also what is the consequence of a hotspot. And I need to believe that having, again, that same copper, let's call it diffuser, so to speak, or cooling down, or just the fact that copper melts at, I don't know, 4 times the temperature of plastic, not only there is less risk, but there is also less, let's say, consequences, if we want to put it that way. So, but you're correct.
Okay, certainly.
Yeah,
thanks a lot.
If I could add there, also due to the pattern of the contact with all these different spots, even in the unlikely case that there would be a cell cracking, the risk of hotspot formation is much lower. That's due to the layout of the contact pattern.
Yes, and in addition, let's say in MWT, maybe this is the case that the hotspots are occurring, but in the IBC cell, actually, because the P+ and N+ is touching. So actually, even if you have, let's say, a breakdown in the zebra cell, that means that the zebra cell is more or less heating at the whole area and not in the hotspot. So actually, in the zebra cell, there is already a prevention for the hotspots.
Okay. Sure, and Hugo, you mentioned in your presentation the possibility of back contact being particularly suitable for thinner wafers. Is this something we might see in the next few years?
Yeah, absolutely, and of course the driver is with the cell makers for this, but we can enable it together with our partners in the ecosystem. So we have partners who can also produce demo modules together with us, and we supply the backsheet, and we can do it on their equipment. So absolutely.
Okay, certainly. Yeah, that would be an interesting development to see. Okay, and sticking with the manufacturing processes, this is probably another question for Hugo. Do you, with the conductive backsheet, do you require any treatment of the surface before you can apply the conductive adhesive or paste?
No, that's not necessary. So with the backsheet is supplied in boxes, and with the equipment of the assembly line producers, they're picked up and put on the production line without further pre-treatment.
Okay, yeah, I think that makes sense. Okay, and well, we are coming up to the end of our 1 hour slot, but time for one more question. Do we see? I mean, we've talked a lot today about rooftop markets, and I believe Radovan touched on this in your presentation on the utility scale as well. But do we see back contact coming to large scale as well as rooftop markets?
Yes, it can happen, and I believe that it has to be connected with bifaciality as well. So IBC can be also bifacial, even if you have the contacts on the rear side, and actually conductive backsheet can do it as well. But it's more, let's say, complicated, but we are working on it.
I certainly
Okay, so
I keep saying that this technology is like being a kid with a box of Lego. At this moment, we are just making some very simple solution, but you can really build that pirate ship and be able to utilize the technology, the process, and the product to get into a bifacial and into let's say utility field.
And if I could add to that, it's also a matter of economy of scale. So once we go into this growth that I showed, automatically also the cost price will go down, and it will automatically become more competitive. The largest producer has between 1 and 2 gigawatt production capacity already, so they are going through that curve. And I think, yes, in time, we will become more and more competitive.
Absolutely, it's always an ongoing process of innovation and scale. Okay, folks, I think that is about all we've got time for today. But thanks to all who joined us, who listened in and asked questions to today's speakers. Thanks also, of course, to Hugo, to Paolo, and to Radovan for 3 great presentations this afternoon. You'll see now we have plenty more webinars coming up, so please do join us again. And of course, you can listen back to this webinar and all of our PV Magazine webinars at your leisure at pv-magazine.com/webinars. And coming up when we close down the program today, we do have just a very short questionnaire for our listeners. So please do take 1 minute to fill that in as well. Thank you very much, and we'll see you next time. Thanks again. Goodbye.
Thanks for organizing, Mark.
Oh, you're welcome. Thank you, Hugo.